Imagine you're turning a metal wrench under the hood of your car. You're just trying to loosen a really stubborn bolt on the battery.
Right. Something we've all probably tried to do at some point.
Exactly. But then your hand slips, and the metal wrench in your hand bridges the gap between the positive battery post and the metal frame of the car.
Oh, man. That is a bad situation.
Yeah, it's instant. The tool practically welds itself to the chassis. It sparks violently, turns white hot in your hand, and the battery swells up, basically preparing to explode.
And the crazy thing is that scenario happens in garages around the world, like every single day.
It really does. And avoiding it entirely comes down to understanding this invisible, highly logical language of the machines we rely on. So, welcome to our deep dive.
Glad to be here.
Today, we are spending our time exploring a comprehensive assessment reviewer for automotive servicing. You can kind of think of this as the master guide, the ultimate logic puzzle for professionals who are training to become certified mechanics.
Yeah, and we are going to take a very relaxed, unhurried pace today. We're not going to rush through a checklist today. Instead, we're going to take a leisurely stroll through the garage and really understand how things work.
I love that. No cramming for exams today.
Right. The mission here isn't just to learn how to pass a mechanics test. We want to decode how experts diagnose complex, overlapping problems in high-pressure environments. Because the diagnostic logic required to fix a modern vehicle, it translates beautifully to almost any complex system you encounter in your own life or work.
It really is a masterclass in critical thinking. So, we're just going to look at how things work, piece by piece.
Sounds good. Where do we start?
Well, before anyone even touches an engine block, this assessment reviewer spends a massive amount of time on the physical environment, the tools, and, cultivating a very specific mindset.
The mechanics mindset, right.
Yeah. It demands this intense reverence for precision. For example, it insists on zeroing a vernier caliper before you take a single measurement.
Which seems like a small detail, but it's huge.
Right. The text argues that a tool that isn't zeroed gives you a confidently wrong reading, and that is significantly more dangerous than having no reading at all.
Oh, absolutely. Because if you don't know the measurement, you stop right. You figure it out. But a confidently wrong reading on a caliper gives you false permission to proceed.
To think you're good to go when you're actually way off.
Exactly. In an engine, tolerances are measured in thousandths of an inch. If you measure a bearing clearance with an unzeroed caliper and think it's perfectly to spec when it's actually too loose, you will put that engine back together, and it will inevitably tear itself apart from a lack of oil pressure.
So precision isn't just about, doing a neat job. It's about preventing catastrophic mechanical failure.
Precisely.
Okay, let's unpack this a bit more. It actually reminds me of the way a Michelin star chef treats their knives.
Oh, that's a great analogy.
Yeah, because the reviewer notes that using a wrench size that is just close enough, like maybe using a standard size on a metric bolt, doesn't just mean you're doing a sloppy job. You are actively ruining the ingredients.
Right, you round off the edges of that bolt head.
Yes, and what should have been a standard 10-minute adjustment morphs into this 3-hour nightmare extraction process where you have to drill out hardened steel.
It's the worst. And that same philosophy of anticipating the worst case scenario, it completely dictates the safety protocols too.
Like what?
Well, the manual has an absolute prohibition against getting under a vehicle supported only by a hydraulic jack.
Because it can fail.
Yeah, a hydraulic jack relies on just a few tiny rubber O-rings holding back thousands of pounds of fluid pressure. If one of those O-rings fails, or, if the jack shifts slightly on the concrete, the vehicle drops instantly.
Terrifying. So what's the alternative?
You must always use mechanical steel jack stands and chock the wheels. That way, gravity is working with a physical locking mechanism, not just fluid pressure. You're anticipating the failure of the tool.
Wow, okay. I was reading through these strict safety rules, and one of them actually stumped me for a minute.
Which one?
The manual insists that whenever you work on the electrical systems, you absolutely must disconnect the negative battery terminal first. Not the positive, always the negative.
Yes, the golden rule.
Right, but my initial thought was it's just a circuit.
Yeah.
Does the order really matter that much? It's just a battery. But then I started thinking about how a car is actually wired. And the story of the wrench welding itself to the car started to make terrifying sense.
You put the pieces together.
The entire metal body of the car is the ground path, isn't it?
It is. The chassis, the engine block, every piece of bare metal on that car is wired directly back to the negative terminal of the battery. It acts as the return path for the electricity.
Okay, so if I take my wrench,
Right. If you try to loosen the positive terminal first and your hand slips, the wrench touches the positive post and the metal body of the car simultaneously.
and boom, short circuit.
Worse than a normal short. You have just bypassed every fuse and resistor in the vehicle. Hundreds of amps of raw current dumped directly through your tool.
Because the tool becomes the path of least resistance.
Exactly. But if you follow the manual and disconnect that negative terminal first, you completely sever the ground path for the entire vehicle.
Oh, I see. Once that negative cable is pulled away, the metal body of the car is just inert metal.
Right. If your wrench slips while you're working on the positive side later, it just clinks against the metal frame harmlessly. The circuit is already dead.
That's brilliant. The entire workflow is designed around the logical anticipation of human error. Safety rules in a workshop are written to anticipate failure.
They really are. And that transition from safety and tools to the actual mechanics of the vehicle, it requires that exact same analytical mindset.
So once the environment is secure and the ground path is safely disconnected, we can pop the hood.
Let's do it. Let's look at the mechanical heartbeat of the car,
Yeah.
the internal combustion engine.
Okay, so most of us probably know the basic four-stroke cycle, right? Intake, compression, power, exhaust.
The basics, yeah.
We know the engine breathes in air and fuel, squeezes it, explodes it, and pushes the exhaust out. It's almost like breathing. You breathe in, hold your breath, shout, and then exhale.
I like that analogy.
But what the reviewer dives into is the physics of why these strokes dictate everything about a car's performance. Like, the compression stroke isn't just a setup phase.
Not at all.
Squeezing those air and fuel molecules into a tiny space before the spark plug fires, that's what creates the violent expansion of the power stroke. If you ignite that same fuel uncompressed, it just burns lazily.
Right, it just sort of flares up. Squeezing it is what gives it the force to actually push a 2-ton piece of metal down the highway.
Which is wild to think about.
And the assessment highlights that if a mechanic is diagnosing a lack of power, they immediately look for a loss of compression.
Because the squeeze is gone.
Exactly. If piston rings are worn, or a valve isn't seating perfectly, that squeezed mixture leaks out before it can be ignited. You lose the molecular density required for a strong power stroke.
Makes total sense. And the exhaust stroke is just as important, right?
Equally critical, if the exhaust valve fails to let all those burnt inert gases escape, those spent gases take up physical space in the cylinder.
They just hang around in there.
Yeah, and they dilute the fresh air and fuel coming in for the next intake stroke. That dilution is a notoriously hidden cause of a rough, stumbling idle. The engine is essentially choking on its own unexhaled breath.
Choking on its own breath. That's such a vivid way to put it. Now, containing thousands of those localized explosions, every minute generates a massive byproduct that will destroy the engine block if it isn't managed. Heat.
A tremendous amount of heat.
And managing that heat brings us to the cooling system. The diagnostic clues here in the manual are just incredible.
Oh, they're fascinating.
I was reading a section on exhaust smoke, and it mentioned that noticing a sweet smell accompanying white exhaust smoke is a massive warning sign.
A huge red flag.
But wait, a slight smell coming from a car sounds kind of pleasant. Why is that the ultimate red flag for a mechanic?
What's fascinating here is that engine coolant has a distinctively sweet odor when it vaporizes.
Oh, so the sweet smell is actually burning antifreeze.
Yes. If you're seeing thick white smoke and smelling that sweetness out of the tailpipe, it means the cooling system has suffered a catastrophic internal breach.
Oh, wow.
The coolant is no longer staying in the water jackets surrounding the engine. It's actually leaking directly into the combustion chamber where the explosions happen.
So it's not just like a puddle on your driveway.
No, much worse. It means the gasket sealing the top and bottom halves of the engine, the head gasket, has blown out, or the metal block itself has cracked under the heat. The engine is literally trying to combust its own coolant.
That sounds incredibly expensive.
Very. An external leak, like a puddle on the driveway, is usually just a worn hose or a failing water pump seal. Those are simple, accessible repairs. But an internal leak, you have to tear the entire engine down to the block.
So mechanics just use that one sensory clue, that's the sweet smell, to instantly categorize the severity of the failure. That's amazing.
They use the environment to rule out suspects, too. There's a diagnostic elegance to it. For example, using vehicle speed as a clue for cooling issues, rather than just looking at the temperature gauge.
Yes. The manual has this brilliant breakdown of diagnosing overheating based entirely on how fast the car is moving.
Walk us through it.
Well, if a car only overheats while idling in traffic, but the temperature drops back to normal when you get on the highway, it points to a completely different component than a car that overheats at highway speeds.
Exactly, because when you are driving at highway speeds, you have a massive volume of ambient air ramming into the front of the radiator, naturally pulling heat away from the coolant.
You don't even need the electric cooling fan to do anything.
Right. So if the car only overheats at a dead stop, you know the mechanical circulation is fine, but the electric fan has failed to pull air through the radiator when the car is stationary.
But if it overheats while you're doing 70 miles an hour down the highway, all that natural airflow isn't helping at all.
Which tells you the heat isn't even making it to the radiator.
You have a deeper circulation issue.
Mm-hmm.
Like maybe the thermostat is jammed shut, or the water pump impeller has disintegrated, trapping the boiling coolant inside the engine block.
Yep, the fluid just isn't moving. Now, those perfectly timed explosions, the precise management of fuel, and the cooling fans that keep the temperatures in check, none of that functions without a spark and a trigger.
Right, which brings us to the electronics.
The mechanical systems are entirely dependent on the vehicle's electrical nervous system. And this is where the diagnostic logic has to become completely abstract because, well, you can't see electricity.
You really can't.
Yeah.
You have to rely on your instruments like a multimeter, but you also have to understand what those instruments are actually telling you.
That's the key.
The manual talks heavily about battery maintenance. It points out that the white or greenish crusty powder you see on battery terminals isn't just an ugly cosmetic issue.
Not at all. That corrosion acts as a physical insulator.
It adds massive electrical resistance to the circuit. So a perfectly healthy battery can fail to start a car simply because that crust is blocking the current from leaving the post.
And testing that battery requires a deep understanding of load versus static capacity. The text heavily emphasizes the difference between static voltage testing and load testing.
What's the difference in practice?
Well, a multimeter might show a static reading of 12.6 volts on a battery just sitting there, but a battery with internally degraded lead plates can hold 12.6 volts at rest and then completely collapse down to 8 volts the second you ask it to power a heavy starter motor.
Oh, I see. It's like asking a friend if they feel strong today. They might say yes while they're sitting comfortably on the couch.
Sure.
But you don't actually know the truth until you ask them to help you carry a heavy refrigerator up a flight of stairs.
That's exactly it. The load test is the refrigerator. The mechanic applies a heavy electrical demand equal to half the battery's cold cranking amp rating for a sustained 15 seconds.
Putting it under real stress.
Right. If the voltage holds steady under that intense pressure, the battery is genuinely healthy. If it drops off a cliff, those internal cells are weak, regardless of what the resting voltage indicated.
The reviewer applies that same rigorous skepticism to testing the wiring itself. A lot of people grab a multimeter and just check for continuity, which is essentially sending a tiny trickle of electricity down a wire to ask, is there an unbroken path from point A to point B?
And if the meter beeps, they assume the wire is perfectly fine.
But the source says continuity is a dangerous trap, and you must do a voltage drop test. I was trying to picture this, and it really makes sense if you think about water pipes.
The water pressure analogy is perfect for this. A continuity check is like pouring a cup of water down a massive 10-inch pipe.
Right.
If even a tiny trickle makes it to the other end, the continuity test says the pipe is clear. But if that pipe is 99% clogged with mud, it won't be able to handle a fire hose hooked up to it. It will back up immediately.
So one single microscopic strand of unbroken copper wire inside a deeply corroded battery cable will beep for perfect continuity on a multimeter.
Yes, it will trick you.
But when you try to pull 200 amps through it to turn over an engine, that single strand creates a massive bottleneck. The voltage drop test actually measures how much electrical pressure is being lost across that connection while the circuit is actively working under a full load.
It isolates the exact location of the hidden corrosion. And because vehicles today are essentially rolling networks of computers, mastering these electrical tests is non-negotiable.
Here's where it gets really interesting, though. The ultimate diagnostic tool in the modern bay, OBD, or onboard diagnostics.
The famous check engine light.
Yeah. I always think of an OBD code like a doctor's intake chart. The chart tells the doctor the patient has a severe cough and a fever, but the doctor still has to pull out a stethoscope and actually examine the patient to find out if it's a common cold, pneumonia, or allergies.
That's a great way to look at it. An OBD code might say cylinder 3 misfire. It names the symptom area. But it does not tell you if the misfire is caused by a bad spark plug, a clogged fuel injector, or a mechanical loss of compression.
The diagnostic scanner points you to the correct zip code of the problem, but you still have to knock on the doors to find the culprit.
Exactly. And the manual includes a vital warning about how technicians handle these scanners. It strictly prohibits clearing codes prematurely.
Now wait, if my check engine light comes on, why shouldn't I just clear the code to see if it was a random fluke? Why is clearing it a bad idea?
Because clearing a code before diagnosing it is essentially destroying a crime scene.
Destroying a crime scene, wow.
Yeah, when a modern engine control module detects a fault, it doesn't just turn on a dashboard light, it captures what is called freeze frame data.
What's that?
It takes a digital snapshot of dozens of sensor readings at the exact millisecond the fault occurred. It records the engine RPM, the exact coolant temperature, the vehicle speed, the engine load, and the fuel trim data.
So you capture the exact environmental conditions of the failure. You know, if the misfire only happens when the engine is freezing cold and accelerating versus when it's hot and idling.
Exactly. By erasing the code to see if it comes back, you permanently delete that freeze frame data. You force yourself to diagnose an intermittent problem completely blind.
That makes so much sense.
Furthermore, OBD doesn't monitor everything. It's incredibly sophisticated for emissions and powertrain sensors. But if you have a mechanical grinding noise in a wheel bearing or a pulsating brake pedal from a warped rotor, the computer is completely unaware. You still have to perform a rigorous hands-on inspection.
And even when dealing with the electronics, the manual urges mechanics not to get lost in the complexity. There's this fantastic expert tip in the text.
About intermittent electrical issues.
Yeah. When a sensor or an electrical component works intermittently, like sometimes it's fine, sometimes it completely dies, people almost instinctively blame the expensive computer module.
It's a common trap.
But the manual trains mechanics to aggressively suspect the ground connection first. A slightly loose ground wire vibrating over potholes will cause the power to flicker, completely mimicking a dead computer. You always check the foundation before you assume the roof is caving in.
And taking all of this, the safety mindset, the mechanical thermodynamics, the electrical abstractions, and applying it under pressure requires a really rigid workflow.
So what does this all mean? How do mechanics avoid getting overwhelmed when a car comes in making like 3 different awful noises at once?
That's where the final sections of the reviewer come in. They focus heavily on preventive maintenance service, or PMS, and real-world diagnostic flows.
Right.
A PMS inspection is not casually walking around the car looking for obvious leaks. It is a strict exercise in task management. The manual explicitly grades technicians on their sequence and documentation during a PMS.
They follow an unvarying algorithmic path around the vehicle, right?
Yeah.
Checking fluids, belts, filter restrictions, tire tread depth, brake pad thickness.
Every single time. If you perform a flawless physical inspection, but fail to document a component that is 80% worn and will need attention in the next few months, you fail the evaluation.
Because the whole point is to catch the microscopic leak in the radiator hose before it bursts on a remote highway.
Exactly. And when preventative maintenance fails, or a vehicle arrives with a complex set of complaints, mechanics rely on a highly disciplined mental framework. The reviewer outlines an exercise called the oral questioning drill.
I found this part fascinating.
Yeah. Trainees are given a symptom and must verbally walk backward through the system architecture to isolate the root cause without jumping to conclusions.
Let's walk through one of those. Let's say a car comes into the bay with a starting issue. You turn the key and nothing happens.
Okay, the technician listens. If there is absolutely zero sound, no clicking, no humming, they don't start unbolting the starter motor. They work backward. First, is there power in the system at all? They check the battery static voltage and the main ignition fuses. If those are perfect, they check the ignition switch itself to see if the signal is even being sent.
But what if they turn the key and hear a loud single click from the engine bay, but the engine doesn't turn? The logic tree branches in a different direction, doesn't it?
It does. That single click usually means the ignition switch works, and the starter solenoid is successfully engaging the gear, but there isn't enough power to actually spin the heavy engine block.
So then what?
So they load test the battery. If the battery is strong, they do a voltage drop test on the heavy cables leading to the starter to find hidden corrosion. If the cables are clear, only then do they condemn the starter motor.
It's a relentless process of elimination. And that discipline becomes a matter of life and death when a customer comes in with overlapping symptoms.
So absolutely.
There's a scenario in the text where a driver reports a soft, spongy brake pedal and a terrible metallic grinding noise coming from the wheels. Now, the instinct for an untrained person might be to assume they are the exact same problem. The brakes sound terrible and feel terrible, so just replace the brakes.
Right, but a trained mechanic knows those symptoms originate from two fundamentally different physical failures, even though they occur in the same system.
The grinding noise is a mechanical friction issue. The consumable friction material on the brake pads is worn completely away, and the metal backing plate of the pad is gouging into the metal brake rotor.
Yeah, but a soft, spongy brake pedal that sinks to the floor under your foot, that is a fluid dynamics issue.
Because hydraulic fluid cannot be compressed.
That's how brakes work. You push fluid through a line and it instantly pushes a piston at the wheel. But air can be compressed. If the pedal is spongy, it means air has boiled into the brake lines, or the internal seals of the master cylinder are failing, allowing pressurized fluid to bypass the piston.
So if a technician just slaps new brake pads on to fix the awful grinding noise, the customer pays their bill and drives away happy because the car is quiet again.
But they haven't actually fixed the real danger.
Right. Because the technician assumed the symptoms were linked, they never addressed the hydraulic failure. They have essentially hidden a massive safety hazard behind a cosmetic fix. The first time that customer needs to panic stop on the highway, that spongy pedal goes straight to the floor and the car doesn't stop.
If we connect this to the bigger picture, it shows why you must trace every individual symptom to its unique root cause. You cannot allow the loudest, most obvious symptom, the grinding noise, to distract you from the quiet, deadly failure of the master cylinder.
That is the true art of diagnosis. It is deeply analytical, resisting the urge to guess, and insisting on verifying every link in the chain.
It's methodical troubleshooting at its finest.
Over the course of this deep dive, we've decoded a very different way of looking at the machines around us. Fixing a complex system isn't about brute force, and it isn't about memorizing a list of parts.
Definitely not.
From understanding why an unzeroed caliper is more dangerous than an unmeasured gap, to mapping the exact sequence of a battery disconnect to prevent an explosion. We've seen how the molecular physics of a compression stroke rely entirely on the electrical integrity of a ground wire, and how a methodical, algorithmic approach cuts through the overwhelming chaos of multiple failures.
It's incredibly relevant beyond just cars, too.
It is a powerful masterclass in methodical troubleshooting, especially in a fast-paced world that constantly pressures us to just guess, throw a new part at a problem, and move on.
Think about the onboard diagnostics of your own life or work. When a sudden issue pops up, when you feel burnt out, or a project starts inexplicably failing, are you just plugging in a scanner and quickly clearing the warning codes to make the uncomfortable blinking light go away? Or are you taking the time to look at the freeze frame data, analyzing the exact conditions that triggered the fault, and doing the hard work to find the root cause so the same breakdown doesn't leave you stranded tomorrow?